Okay, thank you, Donghan. Thank you for the invitation. I'm very honored to talk about my recent works in the string theory, gravity, and cosmology 2022 meeting in APCTP, where I have been studied for about 2.5 years since 2015. I changed the title a little bit, but basically it's a talk about how to probe the primordial black holes by the induced gravitational wave. And here is the content. I will briefly introduce what is the importance of the stochastic background gravitational waves. And so the induced gravitational waves are connected to the primordial black hole and some recent hot topics I will focus on later. So here is the space-time diagram of history of the universe. We have the quantum creation, maybe something unknown, and the inflation, then the hot universe until the cosmic microwave background. And then the photons can be freely freely travel to our telescopes. So that's the reason why we can see this beautiful CMB and isotropies here, and to deduce the early initial conditions, which can be the seed for the large-scale structure, which form these galaxies clusters later. But before that, I think the only thing, maybe besides neutrinos, I didn't mention, but maybe the only thing that can penetrate the screaming of the cosmic microwave background is the gravitational wave, which was just discovered like 8 years ago. We have the gravitational wave from the binary black holes of neutron stars and so on and so forth. That's what we have today. But we already know that there must be gravitational waves from the hot universe and even from the quantum origin, which we see these primordial ones or something related to the primordial perturbations of the other types, like what I will talk about as the induced by the scalar perturbation. So as you can see from this figure, that this is a figure of the how this LIGO as interferometer works. It can detect the change of very tiny distances caused by the space-time perturbations propagating from the binary black holes or some other stuff. And what you can observe is the change of the flux for the photons, like this in the Hanford and Livingstone or LIGO, something like this. But for the stochastic background of gravitational wave, you will see something different, something quite like a noise, but it's a little bit different. So I show some result from the Romano and Cornish paper in here. So you can see a noise-like stuff in this black thing. And there's a seasonal kind of signal from the spinning of the Earth with its position relative to the center of the galaxy, because this, in this figure, the stochastic gravitational wave is from the dwarfs. So they have a kind of a seasonal modulation like this. But in general, you can have many different other types of stochastic gravitational waves. So here I listed a few of the future projects or current projects, which are aiming to detect such stochastic gravitational wave as at least one of their main scientific goals. Like this is the space interferometer of China, Taiji, and in Europe we have LISA, and this is Chinese telescope of the FAST. This can kind of monitor the positive timing arrays. We have the CAGRA and SK and so on. So here is a little bit basic quantities of what I will talk about. So when we look at the space-time metric, we have a metric like this in the conformal Newton gauge, not conformal, just Newton gauge. So we have these Newton potentials, which are connected to each other. If there is no anisotropic in the matter content, then these two kind of things are just equal to each other in their amplitude. The energy density of the gravitational waves and the so-called long wavelength approximation is something like this, and related to the power spectrum or the tensity perturbation of the tensor perturbation by this. So to compare with some other components, like the energy density from the other components to the universe, cosmologists usually use these so-called spectral energy density defined in this way, normalized by the critical density like this. So this is connected to the power spectrum of the tensor perturbation by a factor of something like this, which comes purely from the definition under the long wavelength approximations in the far field region. Anyway, so the equation of motion for the tensor perturbation is given by an equation like this, where the source term is kind of projector times the kind of energy momentum tensor, which is proportional to something like this. So you can see that it's a kind of a quadruple form of the velocity of the source. So this kind of a quadratic form can be binary black holes, cosmic strings, bubble walls, primordial magnetic field, and the scalar projection, and so on and so forth. So they have many, many different types of sources, which can form different types of the spectral shape for the tensor perturbation, and so for the gravitational waves. For instance, I list a few of them here. So binary black holes, cosmic strings, colliding bubbles, and eddies in the phase transition, extragalactic magnetic fields, and some extra scalar fields beyond standard model, so on and so forth, and the moving fluid in the primordial fluid of the universe. Anyway, so here is a kind of a schematic diagram of how these gravitational waves will be like in the diagram of the omega GW, the spectral energy density versus the frequency. So we have a very long frequency range where we have the primordial gravitational waves from inflation and gravitational waves from cosmic strings, the first order phase transition, scalar induced gravitational waves, which I will focus mainly in this talk, and incoherent superposition of gravitational waves from the band. For instance, the primordial gravitational from inflation is highly suppressed because of the we already observed the scalar perturbation, and the tensor to scalar ratio is very small. So we already know that the amplitude of the main part for the primordial gravitational must be smaller than like 10 to the minus 16. And the only possible hope to detect them is by the CMB B-mode polarization. There are a few experiments like by Sepp array and LICPD, this is one in China, and Lightbird in Japan, to see what's going on for the polarizations. For instance, here is a famous result by SEP2, but it proves that this is just from the dust foreground. It's not the real gravitational wave signal. But if we want to see that, it must be something like that. And in the intermediate region, which is mostly more or less like a scale invariant, we can, if we are lucky enough to see these amplitudes, we can see even more for a different change of the Hubble parameter and the degree of freedom based on some thermal processes. Like for instance, during this QCD crossover and neutrino decoupling, you can see some wiggles on here. But because the amplitude is so small, that it's unlikely that we can see it in the near future. But if we have a blue-tilted primordial tensor perturbation, then things might change. Like for instance, we can have a blue-tilted tensor perturbation, which increases for a few epochs and then just go down. So it is possible even that it might be explained by this recently discovered nanograph signal of this so-called common process. So that's one possible explanation. And a more realistic thing, I think, in the future is to detect the tail of the primordial gravitational waves. This is something that I work with Sasaki-san and two of my students. If we have the low scale repeating, then this tensor perturbation means which has such a small wavelength that never exit the Hubble horizon will stay in the vacuum. So if you calculate the omega GW, it will just explode like frequency to the fourth. But in this case, you have to subtract the vacuum modes for that. So there are a few papers talking about this kind of thing, but if you do it correctly, the result will be like exponential decay. So it's something like this. And exponential decay is difficult to be detected, but if you have a post-inflationary stage where the equation of state is stiff, like for instance, in here, you see the W equals to 1/2, and you might have a stage where the background energy density decays much faster than that of the gravitational wave. So in comparison, the omega GW, the relative energy density of gravitational wave increases after the end of inflation, but lasts for a few epochs until the smallest scale that the never exit horizon appears. So in this case, you might have a kind of parallel enhancement, which is based on the equation of state parameter W, but it will reach some maximum value. And then after it reaches the smallest possible wavelength, it will just exponentially decay. So this kind of signal is possible to be detected in the future. I think it will be very interesting. And we have the incoherent superpositions of gravitational waves. In this case, we have a very long infrared tail of the which is proportional to the frequency 2/3, which you can be seen here, and some wiggles in around the peak, and also exponential cutoff. This kind of thing has been checked carefully by the LIGO 038 data, and they found an upper bound by the recent kind of data analysis. So it's like smaller than 10⁻⁹ at 25 Hertz. This is shown in this paper. And also it's possible to have the first order phase transition where you have different kind of processes like the bubble collision, which generates the gravitational wave in this blue curve, and the sound waves, which is like this green curve, and you have the magnetic hydrodynamical turbulence, which is this red curve. So altogether, you will have something like this. This envelope line is possibly to have a two-peak structure, which shows the size of the bubbles and the size of the eddies inside the bubbles. So this is very characteristic. It's very easy to be confirmed in the future. The next time we will focus on the main part of this talk is the gravitational waves induced by the primordial scalar perturbation and its connection to the primordial black holes. So I already know that this stochastic gravitational wave background comes from the so-called moving fluid. Like this, you have moving fluid, and this fluid have the quadruples. Then the quadruple can generate gravitational wave in this way. So you have the field equation, which comes from this ij component of the Einstein equations, and the source term, as I said, is proportional to a quadruple form of the field velocity, which in the case when it is sourced by the primordial density perturbation, it can be calculated by the 0I component of the Einstein equation. So it's something like this. You can see that this tensor perturbation has a source which is a quadruple form of the scalar perturbation. It's like something like squared. So roughly speaking, you have something like this. Hij equation of motion of Hij has a source of this form. So this is the reason why it's called the secondary gravitational waves in some sense, because the orders of the tensor perturbation and the scalar perturbation are different. And you can solve this equation by the green function method. And it's just the integral of the time of the green function and the convolution of the power spectra of the two of these scalar perturbations, something like that. So roughly speaking, we have omega GW, this relative spectral density I defined earlier at the radiation dominated universe. So it is a constant if it's compared with the critical density in the radiation-dominated universe. It's proportional to the 2-point function of the tensor perturbation in here, which is proportional to the 4-point function of the scalar perturbation. This is Newton potential, but let's say scalar perturbation. And this is the power spectra, the product or convolution of 2 power spectra of the scalar perturbation. And then I transfer the Newton potential to the curvature perturbation in this way. This is just the order 1 component. So for this reason, I have shown that we have this thing, and now I will talk about the origin of the scalar perturbations. So you already know that from the CMB temperature and isotropy, we can reconstruct the primordial scalar perturbation or curvature perturbation in the way that it must be scale invariant at a very large scale, like 100 let's say 0.05 inverse MPC, so something like this. This is the result from Planck 2015. And on small scales, because the lack of resolution, we do not have much information about that. So in this case, it is possible that we might have some kind of enhancement of the scalar perturbation, which can generate the gravitational wave by the nonlinear perturbation I talked about earlier, the secondary so-called induced gravitational waves. This arrow represents the primordial fluid sourced by the scalar perturbation. So we have gravitational wave. That's what I talked about. And this kind of thing can be detected in the future by LIGO Virgo, Kagra, LISA, so on and so forth. And on the other hand, we might have gravitational collapse because we have such a huge perturbation, which is nearly of order 1, then we might have the gravitational wave collapse when it re-enter the horizon. So this gravitational, this primordial black hole can be also detected by many experiments, especially the microlensing or some CMB mu distortion stuff. And these two kind of things can be cross-checked to probe the primordial scalar perturbation. That's the main goal of this research. So now I will talk about the formation process of primordial black holes. So this is a space-time diagram, which you might be very familiar with. This is the scale factor in the logarithmic scale, and this is the physical length in logarithmic scale. So this thick line is the Hubble horizon. So it's a constant during inflation and is proportional to scale factor squared in the radiation-dominated universe. And we have matter-dominated universe and the dark energy so on and so forth. I will focus on this stage, and we assume, as we said earlier, that on the larger scales, it's already determined by the CMB anisotropy like this. But on small scales, we have an enhanced peak by whatever reason, which I will talk about earlier. So in this case, if there is a peak and the lax of the horizon, nothing will happen. Just stay there, because we do not have a very large kind of a causality connection to make these parts know each other. So for instance, you have a density perturbation like this, you have very small horizon size, then basically the sound wave cannot reach each other. So we do not have any collapse during the intel region where the scale of the density perturbation is outside the Hubble horizon. But once it re-enters the horizon in here, then things becomes different because it knows it is a huge density perturbation, or in the language of physics, the density waves can propagate in around all of these horizon size. Then it might collapse if the density perturbation is large enough, or it exists some critical value of order 1 or something. So this is kind of classical picture of the primordial black hole formation listed in these papers by Zeldovich, Hawking, and Bernard Carr. So the one thing that is critical is the so-called critical density. critical density determines how much of the universe can collapse into primordial black holes. So this can only be done by a numerical study, but there are some approaches in analytical research. But I don't think there is a kind of a common knowledge of what we should choose. So just choose something which is over the 1, 0.2, 0.3, whatever it is fine. So after you choose this, then the primordial black hole formation will happen for all of these modes that are beyond this critical density for a given probability distribution function of the density perturbation like this. So this is a Gaussian probability distribution function. Once the tail is beyond the critical density, then it must collapse into a black hole. For many different parts of the small horizons of the universe, you have a small portion of the primordial black hole. Then all of these regions combine together to form our universe. Then you found that our universe, you have many primordial black holes, which might be ordered like matter or LIGO detection or something. That is the main picture. And the formula to calculate this in the simplest way is the so-called Spectral scenario, where you just calculate the integral of all of the probability functions beyond this tail. So this gives you the complementary error function of the delta C divided by the variance of the Gaussian distribution. So you have a abundance of primordial black hole as this high sigma tails thing. And after that, you have some redshift because primordial black hole is a form of matter. So this decays the energy to proportional to the scale factor to -3, which is decays slower than that of the background, which is the radiation that decays as 8 to the 4th. So in this case, you enhance a little bit if you just focus on the relative density. And in the matter-dominated universe, everything is the same. So what is the essential part is to calculate the relative density fraction at the equality. So after that, you can have the final result, which is usually written in the so-called fPBH as the mass function, which is the energy density fraction of the primordial black hole normalized by the energy fraction of the cold dark matter. So it's related to the beta m here by this kind of thing, with a factor which reflects the size of the horizon, because this matters how much it will experience in the radiation-dominated universe. So this is again is the this figure, but I put it a little bit larger. So if we have a variance which is the same as the CMB value, so it's like 10⁻⁵, then you substitute into this formula, you found that the primordial black hole is like exponential -10 to the 10th. So this is completely negligible. This is the for the case that you can extrapolate the power spectrum of CMB scale to the very, very small scales. So if everything is just linear and you believe the running, whatever, so it's the same. But if you want to have primordial black holes to be or dark matter or some kind of observational effects, you have to require the enhancement, as I said. If the variance of the power spectrum of scalar perturbation is enhanced to like 10⁻², then you have a much fatter Gaussian distribution probability function. So you have a larger area beyond this critical density. Then you might have the primordial black hole as all the dark matter, like in this way. So beta is something like this. You substitute this value with this variance, then beta is like 10⁻15. This will give you the fPBH equals to 1 at the observational permitted window, which I will show later. So this will give you that the sigma delta is like 10⁻². Please remember this number. This is like 3 times larger than what we have on CMB scales. And here is a little bit comment on the non-Gaussianity. If we have a non-Gaussian distribution function, then it is possible that even for smaller variance, we still might have the same amount of primordial black holes because of the it is leaned a little bit, so the area beyond the critical density can be made much smaller, much larger. Sorry. So here's some constraints on the primordial black hole abundance. So you have these constraints from all of these experiments. Because my time is limited, I will not explain what it is, but just remember that these colored regions are some kind of excluded. So we do not have any primordial black holes here, but we can have primordial black holes in this window. I think this one is gone too, so we do not have any constraints. So just be here. So in here, you can have primordial black hole as all the dark matter. This is called asteroid mass primordial black holes. And you also have, as you can see, that you have something here where the primordial black hole can be like 10% of the cold dark matter. This is the planet mass primordial black holes. And for LIGO detection, we might have a fraction of the LIGO detection. You know, we have 90 events for the binary black holes. Maybe one or two of them are primordial origin. So it might be like 1% or some, or even larger for the solar mass primordial black holes, or subsolar or whatever. Like this. I will skip this slide. So as I said, the primordial black hole as LIGO events, this is a study by many papers. And it is found that it cannot be all of the primordial black holes. So the maximum value is like 50%. And their best fit is like a few percent, which give you the fPBH is like a 0.1. It's like the 1 2 - 3. It's like written in this way. I think this is the done by this paper. And for this region, this is because you found some ultra short timescale lensing events by the microlensing experiments. In this case, all of these three kind of things, especially the OGO, has found it. In this case, you might explain that to be primordial black hole, or it might be some floating Earth or something. But if it is primordial black hole, then you might have a fraction of like 10% or something like this. But I believe that in the future, because claimed by they said they have the spectral see, you have the all of these constraints in a few years, so which might detect all of these regions in the future. In this region, because of the so-called finite size effect and wave effect, the microlensing experiment cannot work. So this makes this completely undetectable by microlensing experiments. So you can make all of the predictions in here and make primordial black holes as large as dark matter kind of thing. For instance, we have a paper from the primordial black hole from the Starobinsky model. I call it 1 because I will talk about the Starobinsky Model II sometime later. This is a two-field model. You have, in this direction, it is purely the Starobinsky potential. It's like a very flat plateau like there, and you have the CMB and the SGWB and so on and so forth. And after a few EFOs, like 40, 60 EFOs, you have not 60, sorry, 40, 50 EFOs. It will roll down here and you have a few oscillations and go to the other direction by this kind of effective action of this. Then you can have plenty of primordial black hole formation at this transition point. And there are a few similar papers based on this Starobinsky or Higgs Starobinsky model, Higgs R² stuff. The outcome is that on large scales, it is very good with the Planck constraint. This is the benefit of the Starobinsky model. And on small scales, we have the primordial black hole as well the dark matter. So this is a very good twofold benefit. And I will talk a little bit on the Starobinsky Model II. So this is also the Starobinsky model, the single field model with a singularity in the linear potentials like this. So we have a plus phi and a minus phi, which is a little bit different. And usually you have many orders of difference of this a plus and a minus. So you have something like this. This is just a schematic kind of a figure, but actually the actual difference of a plus and minus might be much larger if we want to have a huge enhancement for the density perturbations. So this is studied by a paper like 20 years ago, which one's Lido in here, and recently there are a few papers talking about this again. You have a power spectrum like this, you have a dip, and then there's an enhancement which enhances at most to the frequency to the fourth or k to the fourth, the so-called steepest growth by this paper. And you have some oscillations on that. And you have a plateau-like thing, but you have a smaller and smaller amplitude for the oscillations. This is a prototype of what is nearly called the near inflection point inflation. So this is quite popular for the recent papers talking about the ultra slow rate inflation, because you can have some much smoother power spectrum, which is enhanced for many orders of magnitude like this. This study by these papers too. And so I can see that this Starobinsky Model II is a toy model of this near inflection point or ultra slow stage. So we talked about this a little bit, because in the LIGO paper, you already see that you have enhancement which is proportional to the slow parameter of these two stages. So you have a larger slow parameter here, you have a smaller slow parameter here, then you just combine them together, you have a huge enhancement factor, which is proportional to the A plus divided by A minus square. So you can make this like 10 to 1000 or 1000 or something to meet your need to generate enough primordial black holes dark matter. But actually you have extra enhancement in here, which is quite important. In our recent study, we found that this amount of enhancement is independent of the other parameters of the theory. It only depends on the position of the peak, which is approximated at pi, because this is very easy to understand, because the oscillations come from the mixture of different modes from the vacuum, which is just a combination of the Hanker function of 3 halves or something, or 3 halves or something. So you have many kind of sines, cosines of 2 eta or something. So the period is just the pi. So the first and the largest maxima is around the pi. So if you have this, then you can calculate this factor. It's just less than 3. And we finally find that this is not enough to generate primordial black hole as well as dark matter in the case, because if you just look at the peak, everything is fine. But if you go to infrared a little bit, or in this figure, go to ultraviolet a little bit, the plateau is not enough to evade the extra galactic ray constraints. Because we know that in the primordial black hole constraints, in this region, because the lifetime of the primordial black holes is so short that it is experiencing the serious Hawking radiation or explosion today. So you can have a very huge amount of different particles, in the democratical way. In this case, the most sensitive bound of observation is the optical. So you have the so-called extragalactic gamma ray constraints. Here I only draw one of them, but actually this can go down to like 10 to minus 20. But as I said, this constraint in this Starobinsky model, you have a fixed amount of the height of the peak. So this one is fixed by the parameter, you can tune that. But this amount, the amount of the enhancement of the first peak, is just fixed. It doesn't depend or depend very weakly on the amplitude. So in this case, you cannot tune the relative height of the peak and this plateau here. So this means that you cannot evade the kind of thing. So the only method to save this problem is that we require there will be a very quick exit of the ultra slow stage after the peak. But this is something that we are doing right now, so I will not talk about too much details. Anyway, so let me go to the cross-check stuff. So I said we can cross-check the primordial black hole formation and the induced spectral wave in a manner that you have the induced spectral wave like this. As I said, the omega GW divided by the current fraction of the radiation energy density. This is proportional to the tensor provision, the 2-point function of the tensor provision, and 4-point function of the scalar provision, and the variance of the scalar provision to the fourth. And it is something like this. This capital delta is the density provision, delta rho over rho. So this one also enters the primordial black hole abundance in the way here. So you have fPBH collected to beta like this, and beta is the complementary error function of delta critical divided by the sigma tiered. I add tiered because we have a window function to smooth that, but the difference is very small. So basically they are the same thing. And you can just cross-check the amplitude of these two kind of things. So for instance, you have primordial black hole as or dark matter in here. Then you have the primordial of as or dark matter case induced gravity wavelength here. You can see that it's just in the LISA sensitivity bound. Most of the part is in the LISA sensitivity bound. So you can just detect the primordial black hole as or dark matter in the millihertz space for in the ferrometers. So that's the reason why you can do it like this, which is currently no optical constraints kind of possible. So in this case, if the probability distribution function is Gaussian, then primordial black hole as well dark matter, you have the sigma is like 0.2. So based on the constraint that you have it here. But if you have this formula, then this you can kind of estimate the amplitude of induced gravitational waves. So by in this way, if it is Gaussian, it's like the current radiation density times the power spectrum of the scalar perturbation squared. So this is 10 to the minus 6 times this to the 4th of this to the 4th. So you have the 10 to the minus 9. So this is the mark here, which is like much larger than what is called the LISA sensitivity curve. So which means that you can observe such stochastic curve by by a very large signal to noise ratio. And you can also see it from here that if we have non-Gaussianities, then it will suppress the induced quantum wave a little bit. This is because for the positive non-Gaussianity, it will hugely enhance the primordial black hole formation, as I talked before. Then the variance which is needed to generate the same amount of primordial black hole as well dark matter is reduced. This reduction will be reflected in the amplitude of the induced gravitational wave amplitude like this. So if you keep the primordial black hole abundance the same, so you can see that as you increase the F1L parameter, you have smaller and smaller amount of the gravitational wave amplitude. But there is a limit where the F1L goes to infinity, which I call the chi-square limit, that it is still much larger than the LISA sensitivity curve. So in this sense, you can see that LISA must observe the primordial black hole as dark matter scenario. But you have to post the condition that the non-Gaussianity is of the local type, even if the F1L goes to infinity. If you add some other orders, as you know that the probability distribution function can be any type, then you lose your predictivity. I will talk about how to realize this chi-square limit in the last part of the talk. As you might guess, that is in the Curvaton scenario. So this is the third part of the talk, some recent topics. The first one is the spectral shape of the induced quantum wave. Because we know that all of these kind of things has an infrared scaling of the frequency to the cube. This is only depends on the thermal history of the universe. If it re-enters the horizon when the universe is radiation dominated, and plus some other conditions, but the main condition is like this, then you might have this frequency to the cube infrared scaling. So you cannot distinguish all of these signals by just looking at the infrared tail. The only thing to distinguish them is by looking at their peak. That's the key point. For instance, if you have a delta function like scalar perturbation, the induced quantum wave will be something like this. It's very characteristic. But actually, you do not have an infinitesimal width of the peak. So in the real case, you usually have a width of something like, in this case, width is like 0.1. Then in this case, if we invoke the multi-field inflation, then it is possible. But for single field inflation, as I have shown before, you have the steepest growth of k to the fourth, like in the ultra slow roll thing. The width can never be smaller than of order 1. So in this case, in my paper with Sasaki-san last year, we have, those 2 years ago, sorry, we have calculated the induced quantum wave like this. Then we have a result that this is just an error function times that of the delta function. So it's quite the same thing, but with a broken knee here. For delta function, the infrared scaling is always frequency squared, but when you have a width, then you have a far infrared, which is frequency cube, and the near infrared is frequency squared, and you have a same peak behavior here. So once you detect the peak frequency and the break frequency, then you just divide them. You can have the kind of effective width of the peak. So this is very useful relation. So what will happen for the broad peak of the power spectrum? If it is a log normal, but the width is larger or almost larger than 1, then you can see that it's something like this. As the power spectrum of scalar propagation becomes broader and broader, you might have a broader and broader power spectrum for the induced gravitational wave, like this. And we also derive kind of analytical result for the broad peak case. This is very complex, but we have a simpler version that is frequency to the cube in the infrared, and around the peak, it is just a log normal, as in the power spectrum of scalar propagation, but with a little bit different width. This is very easy to understand because if you just times these two power spectra of the scalar propagation together, then this 2 disappears, and you have a new width, which is the previous width divided by square root 2. The second topic is the previous title, the induced gravitational wave from the Curvaton scenario. So you have the, as I said, you have the induced quantum wave, which is suppressed mostly by the chi-square limit of the non-Gaussianity. But can we realize this chi-square distribution in the real world? And the answer is yes, in the Curvaton scenario, of course. The Curvaton scenario is like this. You have the inflaton field, which is just the background, but contributes nothing to the perturbation. But there is a Curvaton field. It contributes nothing to the background, but it can be converted to the curvature perturbation after its decay. It has a very huge amount of the entropy perturbation. But after it decays, it's just transferred to the curvature perturbation at the curvature decay case. So after the inflation ends, it just oscillates around the minimum of this curvaton. It's just like something like matter. So it's proportional to the a to the minus 3. Then you have a just the increasing relative energy density of the curvaton. So it's omega chi like this. The key point is the omega chi at the curvaton decay. So this determines everything. Roughly speaking, it is just, I just write it in the parameter of R. Small r is, roughly speaking, is just this energy portion of the curvaton at its decay time. So this is the most important parameter in the later discussion. Before the curvaton decay, we do not have any curvature perturbation, but after it decays, the entropy perturbation brought by the curvaton will be transferred to that of the curvature perturbation. And the equation of motion for the curvature perturbation and the density perturbation delta is very complex, but in principle, you can solve that, right? So this delta is the curvaton field contrast in the specially flat gauge, and it will transfer to zeta. Zeta is the curvature perturbation in comoving gauge. Anyway, so you can just connect these two. And in the Curvaton scenario, zeta is always connected to small delta, and then you can calculate the primordial black hole formation by the so-called chain law of the probability distribution functions. The probability distribution function of the density perturbation is connected to the probability distribution function of the curvature perturbation, and this is connected to the probability distribution function of the curvaton perturbation. So it's something like this. And the curvaton perturbation has a very good Gaussian distribution function because it's just, by definition, it's just a Gaussian field. And then you can solve the equation I listed here. So you can find the relation of the Curvaton field provision and the curvature provision. So it's something like this. The key point is that you have a nonlinear relation with the curvature provision and the density provision. But if the peak is very narrow, then you can transfer the local relation, non-local relation into a local relation by transferring to the Fourier space. So nabla squared is just like K peak squared. Anyway, you have all of these things, then you substitute into the formula to calculate how much is the beta function and the frequency and the mass function of primordial black hole and so on and so forth. The result is something like this. I will show it in the two-dimensional form later. And the power spectrum can determine the induced gravitational wave thing. Let's calculate this power spectrum. So this is something like this. And you can expand it up to second order. So it's in this manner, because we know that delta is very small, right? And the variance of zeta then is just something like this. In the small r limit, which we are most interested in, you have a very interesting relation that the variance of the curvature perturbation only depends on the combination of square root of r times the variance of the Curvaton field. So it's this combination which determines everything. And then I draw a diagram of R and sigma naught. Sigma naught is the variance of the Curvaton field. These thick lines are the variance of the curvature perturbation, which determines the PBH formation and the induced quantum wave amplitude. So you can see that this colored region are kind of the primordial black hole abundance, which is in this small amounts of color, the primordial black hole can be all dark matter. So it's just around here. And you can see that it's very thin strip. And this can determine almost uniquely the amplitude for the curvature perturbation and also the other kind of stuff.
Okay, you have 3 minutes.
Okay, thank you. So in this R goes to 0 limit, we call the strong non-Gaussian limit. You have this expansion like this. And in this R goes to 1 limit, interestingly, it doesn't go to the linear thing, but it goes to the so-called logarithmic limit, where zeta is what two-thirds times the logarithmic 1 plus the Curvaton provision. This is the same as ultra slow roll. It's called the Gaussian tail, because if you just go use exponential, then you see that delta is proportional to exponential of zeta. So this is quite interesting. And we are going to study that sometime later. And we also check the so-called LISA serendipity that this primordial black hole as dark matter in the Curvaton scenario can be cross-checked by the LISA tension stuff, and everything is fine. And we can, in this case, we can freely reach the chi-square limit by requiring that the R parameter goes to 0. So you can see that is here. And even if it goes to 0, it's always much larger than the LISA sensitivity curve. And we can see that in this scenario, the primordial black hole as dark matter must be detected. So here is a summary. We have primordial black hole abundance on the induced quantum wave can be cross-checked. If you have a primordial black hole as well the dark matter in this window, then you can always have a gravitational wave spectrum in the LISA sensitivity curve, which must be or can be or must be, depending on the shape of your non-Gaussianity, detected by the future plans. I think I will just stop here and take questions for a few minutes.
Okay, we have time for a couple of questions. Anybody has any question?
Hi, Professor Shi Pi. I have a question about, you mentioned the CMB spectrum for the result of an anisotropic universe, right? And can that be used to constrain the gravitational wave?
I talked about the CMB anisotropy, but I didn't talk about the anisotropic universe. This is, but your question is interesting. Yeah, if you assume that our universe is anisotropic, for instance, we have a kind of a preference direction, then I think you cannot see that in the stochastic background of the gravitational wave, because that is only the monopole. But if you go to the dipoles or some other kind of more, we see this is called the anisotropy of stochastic gravitational wave background. If you go to that, then you might see something. I think there are many papers talking about this to detect the anisotropies of the gravitational wave background. But I'm sorry, I'm not an expert on this thing. Yeah.
Okay. Another question is about the fPBH, the ratio of the primordial black hole. Can you explain more how to calculate the fPBH or the gravitational?
I think I already talked about that in more details, but yeah, if you how can I say, you can check these papers actually. I listed here. Yeah, I listed a few, but these papers are quite old. If you want to follow this, you can look at Bernard Carr's recent review. Yeah. I cannot teach you how to calculate in a seminar talk, but you might go to the Bernard Carr's paper to see that.
Another
Okay, sure.
Okay. In this page, you showed the A star. Is it means the primordial black hole is formed in A star time, but show in our universe in the?
No. It's formed in this A re-entry. I think I have shown it here. The primordial black hole can only form when it can feel each other, that my perturbation is much larger than one, not much larger than my perturbation is of order 1. And in this region, the horizon is very small, so we cannot know that. It's kind of a, yeah, it's the language of the density waves. You do not have enough time for the density waves to propagate in the entire density region, right?
Okay.
But in this case, you can. In this case, horizon re-entry, the horizon is much larger, so you can communicate each other and you can collapse.
Many thanks. Thank you.
Okay, I have a short question. In the beginning, you applied the Newtonian gauge for the scalar perturbation, right? Phi and psi, right? And is it going to be changed? Yes. I mean that your result is going to be gauge dependent on the scalar perturbation? If you choose,
that's a very good question. Yeah, I try to avoid talking about that because my time is limited. Yeah, this induced gravitational wave is gauge dependent. I mean, in the second order, you do not have a gauge invariant quantity in perturbation theory, right? Yeah. So usually, if you choose a different gauge, in some sense, you have different kinds of gauges. In some kinds of gauges, the result does not change. When we say that it's a good gauge, but you might go to some other bad gauges where you can have different results, and something, in some case, the induced quantity wave will diverge. We believe that this Newtonian gauge is good, and the quantity we have calculated is physical. Yeah. Okay. For the reasons, you can check the Sasaki-san's paper with Guilhem. Okay. They have the paper talking about that.
Okay, yeah. Time's up. So let us stop here. Let's thank to the speaker again. Yeah.
Okay, thank you very much.
Thank you. Yeah. Okay.